Hello，
Hello， 老师。
Hello. Let's start our class.
OK， 老师。
Okay.
And today I introduce something about the hex file. After we made the program and compare the program to the hex file, and I introduce something about the hex file.
老师
Yes.
I have a little problem with the chapter 5. A little difficult for me to understand.
You have some problem?
Yeah, with the chapter 5.
Okay.
Input output program. Maybe in the last 5 minutes of the course, just an overview, a brief overview of the chapter 5 again. I tried to go through it this week, but really didn't get it.
Sorry, there's some noise. I cannot hear you.
Hello?
Hello.
Archie, please, can you hear now?
Would you like to text me with the on the Meet chatting?
Okay.
Okay.
All right.
Any question?
Okay, Archie, have you seen it?
After class, you want to get over the chapter 5
again.
chapter 5.
Yeah.
Oh, okay.
Okay. Thank you.
No problem. Because the assembly language program, if you want to know how to make a program, and maybe you need to do some exercise. So there is more PPT about the assembly language, but I rearrangement the class. I give you some important. So and I give you something about the hex files, and then after that I will introduce some function. In for the 8051. 8051. Yeah.
Okay, Lash, thank you.
Okay. Hardware connection and the intro hex file. 8051 family have 40 pins. And there's some pins IORD WR address or some date interrupt. This is the pins for the different functions. The 8051 there's many different package for the DIP, QEP, and the LEC different package some companies provide 20 pins 20 pins version of the 8051 with a reduced number of the I/O port for less demanding application we use the standard 8051 this 8051 pins I have introduced before, so I don't introduce. This is some pins maybe you need to know. P1, P3, P0, P2, P2. This is for I/O. This PSEN for external memory. ALE for the address. RAST reset the microcontroller. GND ground connect to the ground. Here is for crystal resonate. Here is VCC. Here is with VPP with EA for external memory or for the write program to the ROM. Here is ARE PSEN. I have already introduced. 8051 has an on-chip oscillator, but requires an external clock to run it. So cause crystal oscillator is connected to the XTL TL1 and XTL2. This is a standard connection for the 8051. So, maybe you have found when we simulated the 8051 in the Pro Tools, we needn't to connect this oscillator extra oscillator because it's the default. It is default. If you use the frequency source other than a crystal oscillator, such as the TTL oscillator, it will be connected to XTL1. XTL2 is left unconnected. Mostly we use this continuation. The speed of 8051 refers to the maximum oscillate frequency connected to the XTL, and 12 mHz chip must be connected to a crystal with a 12 mHz frequency or less. We can observe the frequency on the XTL2 pin using the oscilloscope. Reset pin is an input. Is an active high. Normally is no. Applying a high pulse to this pin, the microcontroller will reset and terminate all activities. So if you applying a high pulse to this pin, the microcontroller will reset. It is often referred to a power on reset. Activating a power on reset will cause all values in the register to be lost. after the microcontroller is resetted, the register will lost the value, become the zero, become to zero, except SP stack point SP is become 07 and the P0 to P7 is become FF. Other register will be other registers will be zero. Will be zero. In order for the reset input to be effective, it must have a minimum duration of 2 machine cycles. It means if you want to reset the microcontroller, you need applying a high level to the reset for 2 machine cycles. 2 machine cycles. In other words, the high powers must be high for a minimum of 2 machine cycles before it's allowed to go no. Allowed to go no. So you want to reset, you give the high level powers for 2 machine cycles. 2 machine cycles. EA, external access, is an input pin must be connected to VCC or GND. The 8051 family members all come with on-chip ROM to store program. The EA connected to VCC. Use the ROM, on-chip ROM, on-chip ROM. The 8051 and the 8031 and 8032 family members do not have on-chip ROM. So code is not stored on external ROM and is fetched by 8031 and 32. Here, the EA pin must be connected to a ground, indicated that the code is stored externally. So, okay.
老师, so you mean the EA is only used for 8031 and 8032? It's not used in 8051?
The EA is valued in 8051, 8031, and 8032. But the function is all the same because there is no on-chip ROM on the 8031 and 8032. So
Yeah.
the pin, the EA pin, is connected to the ground. Connected to the ground. For this connection tells the microcontroller the program is stored on the external ROM. External ROM.
So we can use EA in 8051. That's my question. We can also add external ROM to 8051.
851, yeah.
Okay.
If you want to the external ROM,
Okay.
do not use the on-chip ROM. You connect the EA to the ground.
Okay.
Yeah.
Thank you.
That's okay. The following 2 pins are used mainly in 8031 based systems, mainly in 8031, but also used in 8051. 51. PSEN program store enable is an output pin. This pin is connected to the OE pins of the ROM. 80 pin of the ROM. ALE address latch enable is an output pin and is active high. P0 provides both address and date. We need to remember this. P0 provides both address and date. The 8031 multiplexes address and the date through the port 0 to save pins. ALE pins used for the multiplexing the address and date by connecting to the G pins of the 74LS7 373 732.
So
This is yeah.
The ALE is only used in 8031. We don't use it in 8051.
Oh, you can use this on 8051 and 8031. It's okay. The serials of 8051 we all can use ALE. ALE is a address latch signal.
Okay.
So we connect this ALE to the G pins of 74LS373 chips. If ALE is valid, the address is knocked in 74LS373.
Okay.
The four 8-bit I/O ports are P0, P1, P2, P3, and each use 8 pins. All the ports upon reset are configured as output, ready to be used as input ports. After the microcontroller is resetted, the port configured as output. Port 0 is designated as AD0 to 87, 80 and 7. A address, D dates are used for both address and date. When connecting an 8051, 8031 to an external memory, port 0 provides both address and date. 8051 multiplexes address and date through port 0 to save pins. ALE indicated if P0 has address or date. When ALE is equal to 0, it provides date. When ALE is equal to 1, it has address. Port 0 can be used for input or output. Each pins must be connected external to a 10K ohm pull-up resistor. This is due to the fact that P0 is an open zone, unlike P1, P2, and P3. Open zone is an term used for most chips in the same way that Open Connect is used for TTL chip. It's the difference between P0 and P1 to P3. So it is special for the P0. You need to use pull-up resistor, 10K ohms pull-up resistor. In 8051 based systems with no external memory connector, both P1 and P2 are used as a simple I/O. 8031 and 8051 based systems with external memory connection, P2 must be used along with P0. Port 2 used with P0 provides the 16-bit address for the external memory. P0 provides the no 8 bits, while A0 to A7. P2 is used for the upper 8 bits of the 16-bit address, designated as A8 to A15, and it cannot to be used for I/O. When P0 and P2 used together, the P0 cannot use as a simple I/O. Port 3 can be used as input or output. Port 3 does not need any pull-up resistor. Port 3 has the additional function of providing some extremely important signals. Additional function. Port 3 has the additional function. This is the additional function for port 3. RxD, TXD for serial communications, INT0, INT1 for the external interrupts, T0, T1 for the timers, WR and RD for read and write signals of external memory, memories. Intel Hex file, is a widely used file format designed to standardize the loading of executable machine codes from chip. Okay.
Lashi, can you go back the previous slide?
Okay.
Yeah. This is port 3, right?
Yeah.
Do you have the explanation for port 2 and 1 also?
Port 2 and 1.
Yeah.
Oh, it's port 2.
No. Like the picture.
This is port 2 and port 1. Port 2, port 1 used as a simple I/O.
Simple.
Yeah.
Output.
Just for I/O. Just for I/O. This port 3 has can be used for the I/O or used for the additional function. Additional function. Yeah.
So which port is the most useful in 8051? This port 3 or port 1?
On port 3, port 1.
Yeah, I said which one is the most useful? Like port 0 and port 1, 2. You said all of them are input output, and only port 3 is the we need to use in like 8 byte. We need to use in different ways, like right?
Oh, port one,
And
it has not the additional function. So normally we use port one as a simple I/O.
yeah, simple.
Yeah,
But
but port three has the additional function. Sometimes we use the additional function. We don't use
yeah,
port three for the simple I/O. Yeah,
okay.
mostly
But
we use
also, you said port 0. Also, you use it for simple input output, right? Port 0.
yeah. Port three we can use that as a simple I/O, but mostly we use the port three use its additional function. Use its additional
Mhm,
function. Yeah.
mhm. Okay, Laoshi. Okay.
Okay. We can review the port one, port three. Port zero used as the address and date. Use the address and date.
Oh yes, Laoshi. Yeah.
Yeah, port
Thank you.
three, port zero use the address and date. Port one can use the as a simple I/O, but port two can use the along with can be used along with P0, provided the 16 bit address. Port 3 can be used as a simple I/O. Sometimes we use the additional function for the this function. If you don't use this additional function, you can use port 3 as a simple I/O. Simple I/O. Here is some introduce about the hex files. Hex files. We want to execute the program. We need to compile the program to the hex files. Hex files. The nodes that comes with every ROM barrel support the internal hex file format. In many newer Windows-based assemblers, the internal hex file is produced automatically by selecting the right setting. The DOS-based PC, you need two utilities called OH to produce that. If we use the hex files on Windows, we need to use a utility produce the hex files. Produce hex files, but some assemblers can produce hex files. For example, when we simulate the assembly language, we use the Protos produce the OH files. The DOS environment, the object files is fed into the linker program to produce as ABS files. The ABS files is used by systems that have a monitor program. Then the ABS files is fed to the OH utility to create the enter the hex files. Hex files. The hex files is used only by the loader of an EEPROM programmer to load it into the ROM chip. Into the ROM chip. This is a hex files. Hex files. If we compile the assembly language to the hex files, this will store the codes like this. First is address location. First is address location. Second column is the code. Binary code. This is the source code. Source code. The hex files provides the following: the number of bytes of information to be loaded. The information itself, the starting address where the information must be placed. If we we have the hex files, the structure in the hex files is like this. It's like this. This is the example. I just tell you some knowledge about the hex files. Maybe you didn't to remember it. You just know you want to execute the programs before you use the program. You need to compile the source code to the hex files. This is something in the hex files. This is some example for the hex files. We didn't to remember it. Okay. Next, I introduce some function in the 8051. In the 8051, the timer programming. The 8051 has two timers counters. They can be used either as timer to generate a time delay or as an event counter to count events happening outside the microcontroller. Use as a counter, use as a timer. Use timer. Both time 0 and timer 1 are 16 bits wide. Since 8051 has an 8-bit architecture, each 16 bits timer is accessed as two separate registers of low byte and high byte. So we know if you want to access the timer register, you need two steps. You need two steps. Access as low byte and high byte. The low byte register is called TL0, TL1. TL timer no. And the high byte register TH0 and TH1. TH0 for timer 0, TH1 for timer 1, accessed like any other register, just like this assembly language, the code. This is a 16 bits timer TL0 TH0 TH1 and TL1 TH1. So if you want to move the digit to the timer, you need two step. You need two step. Both timers 0 and 1 use the same register called TMODs. TMODs. To set the various timer operation set the various timer operation modes modes. TMOD is a 8-bit register. The lower 4 bits are for timer 0. The upper 4 bits are for timer 1. Timer 1. In each case, the lower 2 bits are used to set the timer mode. The upper 2 bits to specify the operation. This lower 2 bits for set the timer mode. The up to bits specifies the operation. Specifies the operation. This is a T mode. T mode. T mode. The high 4 bits. The high 4 bits for time 0. For time 0. This one is for gates. Gating control when set timer or counter only while the INT X pin is high and the TRX control pin is set. TR is set. When cleared, the timer is enabled whenever the TRX control bit is set. CT, timer or counter selected. Timer or counter selected. You can use this set the register working as a timer or work as a counter. Was counter. M1, M3 is the mode setting. Mode setting. There is 4 modes for the timer and register. Mode 0, mode 0, mode 0. 13-bit timer. 13-bit timer. Mode 1, 16-bit timer. Mode 2, 8-bit auto reloaded. After the timer is finished, the value can be auto reloaded to the register. To the register. Mode 3 split the timer mode. Split new time mode. 2 different 8-bit timer. 2 different 8-bit timer. Here is some example for the timers. Indicate which model and which timer are selected for the each of the following.
Lashi,
Yes.
please can you go to the previous slide? I couldn't get it very well. Yeah, please can you explain the modes again, like the modes and the operation?
You want the know something about the mode?
Yeah, I didn't really get it.
Yeah, if we set M1 and then M0 to 00,
Okay.
this timer used as a 13-bit timer.
Okay.
13-bit timer. If we set the M1 and the M0 to 01, this timer used the 16-bit timer. We know the timer originally 16-bit, 16-bit. If we use set to 00, use as 13-bit, so there is 3-bit is lost,
Yeah.
When M01 and M0 is set to 10, 8-bit reload, 8-bit reload. So this timer, the value TH hold a value which is to be reloaded. Reloaded TL each time it overflow.
Okay.
When the timer is overflow, the value in the TH is reloaded to the TL automatically.
Okay.
Here, when M1 and M0 is set to 1, the split timer model, two different, two independent 8-bit timer.
Okay.
Yeah. This model used for only time 0, on time 0. Okay, this is some example for the we can practice for the T mode. If we use this code, move T mode 01H 01H. So after this code is executed, T mode is equal to this value. We can analyze here. If we give the value to 001, which means here is 0, 0, 0, 0, 0, 0, 0, 1, 001. So from here we can see the M1 and M2 is 01, 01. So time 0 is set to 60-bit timer. Yeah. The M1 and the M0 for the time 1 is 00. So we know that time 1 is set to model 0, 16-bit timer, 16-bit timer.
13.
Yeah. Model 1, time 0 is selected. Model 1, time 0 is selected. If we use the this value, we can see that the model is 01, 01. So the model 1 of time 1 is selected here. Yeah. So from here, we know how to set the T mode for the time 0 and time 1. Time 1. This is another example. Find the timers frequency and its period for various 8051 based systems with the crystal frequency this is a frequency for the crystal frequency when CT of T mode is set to 0 if CT is equal to 0, it is used as a timer for the timer delay generation. The clock source for the timer delay is the crystal frequency of 8051. 8051. Sorry, I got the phone. We have a break, okay?
Yes, Lashi, we have a break.
Okay, Lashi, no problem.
Hello,
Hello，老师。
hello. Let's
Hello,
continue our
老师。
class.
Yes, 老师。
Let's see the example. Let's see the example. This example tell us how long the timer how long a timer at one at one and we know the oscillate frequency crystal frequency divide 12 divide 12 is the machine frequency so we can catch the machine time machine time. So this is a machine time every each machine time the timer add one each machine time the timer add one the timer of 8051 do starting and stopping by either software and hardware control. In using software to start and stop the timer when gate is equal to zero. The start and stop of the timer are controlled by the by the way of software by TR TR0 and TR1. The set B instruction started and it is stopped by CLR instruction which means when TR0 TR1 is equal to 1, the timer is running but when the TR is 0, the timer is stopped. This instruction starts and stops the timer as long as gate is equal to 0 in the T-mode register. The hardware way of starting and stopping timer by an external source is achieved by making gate equal to 1 in the T-mode register. From here, we can see when the gate is equal to 0, the timer counter is controlled by software. When the gate is equal to 1, the timer counter is controlled by the external input. Find the value for T-mode if we want to program time 0 and in module 2 use 8051 XTAL for the clock source
Okay.
use instruction to start and stop the timer use instruction start and stop the timer, which means we need to set the gate is equal to 0 So we know equal to 0 use the timer So the model is 10 10. The following are the characteristics and operations of Model 1. It is a 16-bit timer. Therefore, it knows the value of 0000 to FFFH to be loaded into the timer register. Timer register. After TH and TL are loaded with a 16-bit internal value, the timer must be started. This is done by set B TR0 set B TR1. After the timer is started, it starts to count up. Add one. It counts up until it is reached the limit of FFFH. When it gets overflow. From here, we can see the machine cycle is the signal. The machine cycle is the signal. So every machine cycle, the timer is added one by one. When it rolls over from FF to 0, it is set high in a big bit, flag bit called TF, timer flag. Each timer has its own timer flag, TF0 for time 0 and TF1 for time 1. Its timer flag can be monitored. When this timer flag is raised, one option would be stop the timer with the instruction clear CLR TR0 or clear TR1. After the timer reaches its limit and rolls over, in order to repeat the process, TH and TL must be reloaded with the original value. TF must be reloaded to 0. To generate time delay, add the T-mode value register indicating which timer is to be used and which timer model is selected. Note the register T, L, and TH with the initial count value Start the timer. Keep the monitoring the time flag with this code. Get out of the loop when TF becomes high. Stop the timer. Clear the TF flag for next round. Go back to step 2 and load TF and TL again. If we want to start another time. Okay, here is the example. In the following program, we create a square wave of 50 duty cycle with equal portions high and low on the P1.5 bit. Time 0 is used to generate the time delay. Analyze the program. Here, we use the simulation software to check the program. Here is the source. We
Laoshi,
okay.
Laoshi, can you walk us through the circuits you just made? Can you walk us through making the circuits like step by step?
Circuit.
Yeah. The circuit diagram you made, the one in your schematic capture, not the source code, the other one. No. Actually, the Proteus.
This here.
No, Proteus, in Proteus.
In the program, Laoshi.
Program.
Yeah,
This
in
one.
Proteus. In the Proteus program, you made a circuit connection. I was thinking maybe you could help us go through the connection.
Which one?
Laoshi, the Proteus program, Proteus.
Virtuous program.
The simulation program.
You want to this program?
Yes, Laoshi, the other one, the previous tab, the schematic capture. This is source code, the schematic capture. No, Laoshi,
This is source code. Yeah.
yeah, Laoshi, go back to the diagram where the connection was done. Connection of the, yes.
Exactly, yeah.
Nice. Laoshi, this one, can you help us do this? Because now we have the application, so we are following you step by step.
You want me show you how to get this?
Yes.
Okay.
Rest back.
I close this project.
Okay, Laoshi.
New project.
Yes.
We don't change anything. Just next. Finish it.
Hmm.
So you want to pick it's fine. This one is 8051. 8051.
Yeah.
8051 microcontroller. Microcontroller. Double click. Double click. So close this. Put here. Yeah. After you get this, we can double click edit firmware. Edit firmware. Here we just use this one. ASEM bar 51 Proteus. Here. This is assembly language. Assembly language. So from here you can see, write your code here. Write your code here.
Yes.
We just copy the code here. This is a code for the example. For example. The green text is a comment. Is comment. This is a symbol code. A symbol code. So save project. Save project.
Laoshi, can you send us this code on the WeChat page so that we can copy and paste?
You want to copy this code?
Yeah, you can send it to us on WeChat.
I
to-
send you by the Meet chatting.
Okay, yeah,
Okay.
Okay.
Okay. I send
Okay.
you by the Meet chatting.
Okay, Laoshi.
Okay.
Yes, Laoshi, thank you. I got it.
Okay. After I save the project, click here. Menu build. Build project. This show compiled successfully. Compiled successfully. So we can start the simulation. Start the simulation. Here we can run the program line by line. Run the program line by line. Here. The program we can see. This is their output. Is a P 1.5. P 1.5. So if we want to see the output, I stop the simulation and add. Also need scope. Also need the scope here. P15. Now we can see the wave. The wave. It's the signal come from here. The P1.5. P1.5.
Laoshi, how did your signal show up? I've done the connection, but my signal is not showing.
You didn't see the
No.
wave.
Yeah, I didn't see the wave.
You close here
Okay.
is a digital oscilloscope
Okay.
technique. Yeah.
In the debug?
Yeah, in the debug. Here. If you don't see the window, this window,
Yes. Actually, mine, I'm clicking debug, but I can't find the digital oscillatory. It's not
You
here.
you cannot find any what?
I cannot find the digital oscillatory.
Oh,
Chart.
you cannot find the
Yeah. Is it library? Debug.
you
Yeah.
cannot find this.
No. I found that. I'm talking about the last thing you did.
Here. You cannot find this one.
Yeah.
If you cannot see this one,
Okay,
you
I see
can,
it now.
yeah, click here. Debug digital oscilloscope
Okay, Laoshi. Thank you.
that's okay. From here, we can check the program. We can run the program one by one, line by line. So we can check every instruction. Every instruction. I hope you can do as I do when you do your assignment. When you do your assignment. This is okay.
Laoshi, I was running it, and after some time it said internal expeciation access violation in model. It says fatal error.
Sorry.
Okay, Laoshi, no problem. Just
Can you
I'll,
can you say it again?
my digital oscilloscope, it's not it's not showing like yours is showing. It's not moving like, see, yours is showing a movement, but mine isn't.
You mean your oscilloscope
Yeah.
cannot be shown?
Yeah, it's blank. No, it's showing, but it's just blank. Nothing is happening when I run the code.
Oh, yeah, showing is blank.
Yes.
Maybe if you cannot see the wave, I I think maybe there is something wrong with your program. Maybe
Okay.
something wrong with your program, as
Okay.
we can see
Hmm?
when we run this program, you can see the P 1.5 blue red.
Okay.
So you can see there is a square wave. There is square wave.
I'll try it again after class.
You need to check this this pin. Check this pin.
Okay, Laoshi.
If you want to make this program by yourself, you need to know how to get the T mode. T mode. T mode. Time zero. Time zero. Mode one. Mode one. Time zero. Mode one. So if we know that if we want to use this timer as model one, we can see this time 0 model 1 here. So if you want to use this timer as model 1, you need to set M1 and M0 to 0, 1, 0, 1. So here is 0, 1, 0, 1. 0, 1, 0, 1. This is a value for the timer register. This is a value for the timer register. This is a toggle P 1.5 P 1.5. This is a delay delay. I didn't provide the delay code, so I give you the code in the mid chatting. In the mid chatting, you can see the code I send you. Including the delay code. Delay code.
Okay, 老师。
Okay. Delay code here. The delay subroutine uses the time is called time is called. In the delay subroutine, time 0 is started by this instruction. Time 0 counts up with the passing of each clock. With the passing of each clock. Which is provided by the crystal oscillator. As the timer counts up, it goes through the states of FF3, FF4, FF5, until so on, until it reaches FF. After the run over FF, we can get the overflow, and raise the flagging, raising the time flag, raising the flag. At that point, we can use the code JMB, JMB, check the flag, check the flag. Time 0 is stopped by the instruction CLR TR0. The delay subroutine, ends. Delay subroutine ends. The process is repeated. Notice, to repeat the process, we must reload the TL and TH registers, and start the process is repeated. In the example, calculate the count of time delay in the delay subroutine generated by the timer. We calculate the amount of the time delay. Here, the oscillator crystal frequency. If we use this crystal frequency, we calculate the machine frequency. We set the machine frequency. So we can get the period of machine time. Here, that's the machine time. In other words, time 0 counts up each 1.085 mu s resulting in delay is equal to number of counter times 1.085 mu s. The number of count for the rollover is FFR. Subtract FF2, we can get this number of counts. So we add 1 to the setting because of the extra clock needed when it roll over from FF to 0 and raise the flag. It gives 14 times 1.085 mu s. This is a delay for the half of the pulse, For the entire period is twice. So we can, okay.
Actually, I think it's a little confusing. If you can go through it again, it will be okay. I think I don't understand. We are trying to calculate the amount of delay time for the whole machine cycle or just one machine cycle.
The timer at 1 when the microcontroller passing through a machine cycle.
Okay.
So you want to know if the delay time divide the machine time, you can get the how many times
Okay. Machine cycle.
the timer calculate. So after you get the count number you got the count number times the machine cycle, you can get the delay the all time.
Okay.
Yeah, this is precise. This is the maximum value. This is the initial value, and add 1 times machine time times the machine time.
Okay.
So you can get the delay the amount of delay time if you want to calculate in decimal, you can change this number to the decimal and computer again. Let's continue this program on this example. Calculate the frequency of square wave generated on pin P1.5. In the time delay calculation of example number 5, we did not include the overhead. We did not include the overhead due to the instruction in the loop. To get a more accurate timing, we need to add clock cycle due to the instruction in the loop. To do that, we use machine cycle from the table in the appendix as shown below. Here I need to explain it. We don't know we don't have this table. But I tell you this every encode has its machine cycle. So you can, if you you can find the instruction machine cycle from a table. Here is the delay cycle. Here is the delay cycle. We can see this move instruction cost two machine cycle, CPL one machine cycle, equal two machine cycle, SJMP two machine cycle, this is one machine cycle. This is one machine cycle. This one is 14 machine cycle. So
why is it 14 machine cycles?
Here.
No, why is it 14 machine cycles?
Here.
Oh, okay,
we have already calculated the timer on machine cycle. 14
okay.
here.
Okay. Oh yeah, okay.
Yeah, you know. So add all these machine cycle together, we can get the accurate timing. This is the accurate timing. After we get the accuracy time, we can get the machine the wave frequency machine frequency. Find the delay generated by time zero in the following codes. Use both of the methods. Do not include the overhead due to instruction. Do not include the overhead, which means here we include the overhead. Here we ignore the overhead. Just calculate the timer delay. Here is the formation. We can calculate here. Use this equation. We can calculate the delay. The FF subtract the initial value add 1, or this result times multiply times the machine cycle. Here use the equation to get the result. When we calculate the delay in decimal, we just convert the hex to the decimal. Here is another example. Another example. Modify TL and TH in example before to get the largest time delay possible. Find the delay in MS. In your calculation, exclude the overhead due to the instruction in the loop. If we want to get the largest time, we just give the initial value as zero. So we can calculate use this equation as the initial value as zero. So we can calculate that and calculate and get the largest time delay. This timer count from 0 to FFF. The following program generates a square wave on P1.5 continuously using time 1 for a time delay. Find the frequency of square wave. What?
Laoshi, can we use those codes in our software and explain there?
You want to use this codes in the simulation program?
Yeah, in Proteus, yeah.
You want to see me show you how to run this codes? Yeah.
And then after one line by one line, can you just here is written, but we want to see that.
You want me show you? Okay.
Yeah. Not this one, the previous one.
A previous one. You want to see this?
Yes, Lord.
Okay. I show you. Start the debug. Start the debug. So after we start the debug, this is just like the hex file. This program executed start from address 0. Start address 0. 0 is a JMP start. JMP start. So next JMP start. Here is the start. Start. Move tmod #01. Tmod #01. We can see we can open the memory internal. Here is the tmod. Here is the register here. Tmod. After this line is executed, tmod is equal to 0, 1. You can see here T mode
Mhm.
is E01 01. Next next TL TL 0 pound 0 F2H here we can see F2 F2 TMR F2 here F2
Yeah.
we can see yeah, you can see here is also F2 F2 after this one TL F2, so we can this one is executed THFF THFF we can see TH F2 this is for time 0 time 0. Call delay call delay call delay there is two debug mode we can jump over the delay or jump into the delay. Here is a step into or step out we can use the step into or click here click here we step into this subroutine set B TR0 TR0 start the time 0 so here now the timer is started timer is started here again JMB TF JMB TF0 again and check if the time is arrived check the time is arrived here just wait just wait after the time is arrived running the next running the next next clear TF TRF stop the timer stop the timer after stop timer clear the TF clear TF0 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 you can see this value is TF0 TF0 next next so now the program is loop in this next this SJMP here SJMP here this is here here the loop in this here so from here we can see the P1.5 change the status running just running this we can see the here if you see this wave is a 9 you can roll the mouse middle mouse you can roll the middle mouse you can see here here just roll the middle mouse. Middle mouse. Now, you know how to simulate the program?
Yeah, Laoshi.
Yes, Lao Shi.
Okay, okay.
Lao Shi, I think it's time for the second break.
Okay, okay. You can. We have a break. Okay.
Okay, Lao Shi.
Okay.
Okay, Laoshi. Okay.
Sleepy. You know you the person who was talking in the class few minutes. Oh, class. The class, I come and take out back. I think you finish like four nights ago. Did you come back in 2010? I didn't have. You need to attend the class. When you come there, it was here. Oh, come to the where is it? So how to do it? There is more than 300. I'm sure it's fun. Hey. Yo. It's over.
Hello.
Yes, Laushi. Let's continue.
Let's continue our class.
Hello, Laushi.
There are more example. I don't explain it. You can check by yourself. Okay.
Okay.
Right. We'll try our best, Laushi.
Next, I introduce finding the loaded time value. Finding loaded timer value. To calculate the value to be loaded into the TL and TH. Look at the following example. And this is the oscillator frequency. We can use the following step for finding the TH and TL. Divide the design time by the machine cycle. Perform FF subtract the result. This result is n. Where n is the value we got in the step one. Convert the value to the hex. Convert the value to the hex. And divide the value to TL and TH. TL and TH. So we can get the loaded value. The loaded value. Here is an example. Here is an example. What value do we need to load the time register? If we want to have a time delay, 5 ms. Show the program for time 0 and create a pulse width of 5 ms. 5 ms. Since the XTAL is here, we know the machine cycle is here. This means that out of mining machine cycle interval, we must make a 5 ms pulse. To get that, we divided one by the other. We divided 5 ms divided 1.085. We got the value 4,608 machine cycle. To achieve that, we need to load the TL and TH. So we execute this subtraction. Divide this to hex and this high H 8 byte and no H height. No 8 byte. No 8 byte. This example show us how to get the loaded value. Loaded value. This is example. This is an example. This example you can simulate by yourself. This is another example. It's XTL that program generates a square wave. 2K has a frequency pin 1.5 1.5. This is similar to example LAN bar 10, except that we must toggle the bit into to generate a square wave. Look at the following step. T is equal to E divided F. E divided F. So this divide F. F here is F. Two key. So we got the time duration. The duration of square wave. To divide the half of it for the high and low portion of the pulse is 250. 250 divide the machine cycle get the counter number. So the maximum the value subtract this count number, we get the loaded value. So to convert the loaded value to hex. Here is TH and the TL and the TL. Now this is the program as follow. Program is as follow. Here. We can simulate. We can check this program by simulation. Sorry, there's something wrong with my computer. I just I added the code here. Move TL1 EAH EAH move TH1 is FFH TH1 set B TR1 BACK back JMB TF1 BACE CRTR1 CRP CRP 1.5 CRP F1 SJMP GAR AGAR built this project, compiled successfully. This square wave come out of P1.5 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 here P1.5 so right there is no loop in this program, so we just say the one time.
OK，老师。
Okay. You can run this program 9 by 9 by yourself by yourself.
So 老师
Okay.
it means basically we use the T mode to cause a delay, right?
T mode.
Yeah. I mean, basically it's used to cause a delay as in the function.
This T mode, you use the T mode, you can set the working mode for the time 0 and the time 1.
Okay.
Yeah. For
Let's
example,
move on.
for example,
Okay.
here is T mod move T mod 01 01. We can check the T mod. Here is the T mod. T
Yes,
mod
I got it.
0, 1, 2, 3, 4, 5, 6, 7. So if you want you use the time 0, you need to set it here. If you use the time 1, you set here. Set
Yes,
here.
Lashi.
Okay.
Yeah, got it.
This is another example for the generate square wave. I don't formulate. You can do it by yourself. You can do
Yeah,
it by
we'll try.
yourself.
Right.
Here is another example.
Okay.
Okay. Next, I introduce the model 2. Model 2. The following are the caricature of and the operation of model 2. It is an 8-bit timer, so it knows the only value of 00 to FF to be loaded to the timer, the register TH. After TH is loaded with the 8-bit value, the 8051 gives a copy of it to TL. Then the timer must be started. It is done by instruction set B TR0 for time 0 set B TR1 for timer 1. After the timer is started, it is started to count up by incrementing the TL register. It counts up until it reaches its limit. Reach its limit of FF. When it roll over from FF to 0, it set high the timer flag. When the TL register is rolls from FF to 0 and the TF is set to 1, TL is reloaded automatically with the original value captured by the TH register. To repeat the process, we must simply clear TF and let it go without any need by the programmer to reload the original value. This make model 2 an auto-reload, in contrast with model 1, in which the program has to reload TH and TL. To generate a time delay, the T mod value register indicating which timer is to be used, and the timer model is selected. Load the TH register with the initial count value. Start timer. Keep monitoring the timer flag with this code. To see whether it is raised. get out of the loop when TF goes high. When TF goes high, clear the TF flag. Go back to step 4. Since mode 2 is auto loaded, go to step 4. This model used for the repeatedly. So when we want to repeat the timer, we use the model 2. Model 2. Here is an example. Here example. It's the oscillate frequency. Find the frequency of the square wave generated on pin P.0 in the following program. This T mode set. Is 20H. 20H is 0, 0, 0, 0. 2 is 1, 0, 0, 0. You can see here is for time 2. For time 1 is for time 1. Here is for time 0. So we know this program use time 1. Time 1. This is 1, 0. 1, 0. Use the model 2. Use the model 2. 8 bits auto reload. 8 bits auto reload. So move the initial value to TH. Start the timer. Check if the timer is arrived. CPL the state. CPL state of P1.0. Clearing the TF. The timer flag. Clearing the timer flag. Jump back. Here. Jump back here. This is a simple program for use the 8 model 2 8 bits auto reload. The target address of LJMP. In model 2, we don't need to reload TH. Since it is auto reload, now we can calculate the delay time. Is a high portion of the path. Since it is 50% duty cycle square wave, the period T is twice that. So twice that. So this is a square wave period. Square wave period. The frequency is here. We can simulate this program. We can simulate this program. Sorry, we just changed this code. T mode to 20H 啊。move th1.5 set b tr1 back jmb tf1 comma back clear p cpl cpl p 1.0 CLR TF1 SGMP back ACP save build. This signal come out of P1.0 P1.0. So I change this needs here. Simulate. We cannot see. We check this program pmod 21 ph file. st set b tr1 back back gmb. This is no loop here. We just can run this program. We cannot see the square wave. Square wave. If we want to see the square wave, we need repeat. Repeat again. We just need to repeat again. We can see anything wrong with this GMB TF1 back CP. Sorry, I got it wrong here. CPL 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 here. Built. You can see the program. Now we can see the square wave. We can see the square wave. It's a example. Line bar 15. Line bar 14. Line bar 14. You can simulate it by yourself. This is another example. Another example. You can do it by yourself. You can do it by yourself. This is a model 2 example. Example. This is a model 2 example. Next, I introduce the timer used as a counter. Timer can also be used as a counter. Counting events happening outside the 8051. When it is used as a counter, it is a pulse outside of the 8051 that increments the TH, TL register. TH and TL register. The T mode and the TH, TL register are the same as for the timer discussed previously. Programming the timer in the last section also apply to the program it as a counter, except the source of the frequency. If we use it as a timer, the source from the machine cycle. If we use it as a counter, the source from the outside event. The CT bits in T mode register decide the source of the clock for the timer. When CT is equal to 1, the timer is used as a counter and gets the pulse from outside the 8051. The counter counts up as a pulse fed from P14 and 15. These pins are called T0 and T1. This is a part of port 3. Part of port 3. Alternative additional function for the port 3. Here is an example. Assume that a clock pulse are fed from T1, fed from pin T1. Write a program for count 1 in mode 2 to count the pulse and display the state of the TL count on P2 and P2, which connect to a 8 LEDs. Let's see the example the code. Move T mode. Move T mode. Here is the T mode. We can see use the time 1. Use the time 1. The mode is mode 2. Mode 2. And here is 1, which means use the timer as a counter. Counter 1 mode 2. Mode 2. Move TH1 pound 0 clearing TH1 set B P 3.5 make T1 input make T1 input. Again set B TR start the counter back move A TL1 get the copy of TL move P2A display it on port 2 display on port 2 here, which means when the counter is running, show the result on P2 P2. If P2 is connected to a 8 LED 8 LEDs check if the time is finished. JMB TF1 back. Keep doing if TF is equal to 0 equal to 0. Clear TR1 stop the counter stop the counter. Clear TF1 make TF1 is equal to 0 SJMP again SJMP again. Here is the example. Use the counter 1 use the counter 1 as a model 2 model 2 this example need a LED display use need a LED display under the extra pulse extra pulse so we simulate this program next time so much for today. Okay.
Yes, Laoshi. Yes, Laoshi.
Okay. Today's class is over.
Thank
Okay,
you,
Laoshi.
Laoshi.
Thank
Okay.
you.
Thank you so much, Laoshi.
If you have any problems, we'll let you know. Thank you.
Bye bye, Laoshi.
Bye bye.
Bye.